Hi, hello, welcome. This is Discrete Mathematics, and today we are talking about equivalence relations. An equivalence relation is an important concept in relations, which we talked about in our last section. It can be defined in many ways. We're going to define it in terms of partitions, which you can recall more about partitions in chapter 1 when we talked about set theory. Let S be a set of sets such that S is equal to S sub 1, S sub 2, all the way up to S sub n, which we can write in this notation, the set of S sub I, where I goes from 1 to n, where S sub I is a subset of X. This is our notation for subset for all I in 1 to n. So each of these sets in here is a subset of X. If for every I in j in 1 to n, where I is not equal to j, their intersection is empty, so none of these sets have anything in common, and the union of the sets is X, then X is a partition. S is a partition of X. So we're breaking up our larger set into sets of smaller sets that don't have anything in common, where when you unite all of those sets, you get your original set back. So here we are going to do an example. Let X be A, B, C, D, E, F, and I want to write 3 different partitions. There are lots of different options here. I'm just going to choose 3. So S is going to be, maybe we'll do A, B, and C together, and then we can do D by itself, and E by itself, and F by itself. We had this idea of cardinality, which is the number of elements. So this one here has 4 different elements. So we'll do another one. Maybe this time we'll do A by itself, and then everything else together. B, C, D, and E, and F. Maybe for a third one, let's do things a little more evenly. We'll do A and B together, and then C and D together, and then E and F together. So there's another partition. There are lots of different ways to partition, but none of the sets that I have here have anything in common. Their intersection is the empty set, but unite them all together and we're back to A, B, C, D, E, F. All right, that's partitions. Let P be a partition of X. Define X, R, Y to mean that if S is a set in P, then both X and Y belong to S. By this definition, relation R is reflexive, symmetric, and transitive. So we're going to prove that. To prove that something is reflexive, I want to show the definition of reflexive, which is that X are X. And this is because X is an element of S, which is an element of P. So this is reflexive. I want to show that it is symmetric. So I want to show that X are Y and Y are X because X are Y, X and Y are in S, so Y are X. So I want to show that X are Y and Y are X. If X and Y are in S, then Y are X as well. That's symmetric. Last one, transitive. I want to show that X are Y and Y are Z. That implies that X are Z. Because X are Y, X and Y are in S. And then because Y are Z, Y and Z are in S. So X, Y, and Z are in S. So therefore, or hence, X are Z. We are setting all this up for our definition, which is a relation on X is an equivalence relation. Equivalence relation on X if it is reflexive, symmetric, and transitive. So we had something was a partial order if it was reflexive, antisymmetric, and transitive. Now we're having a different package, so to speak, and that is reflexive, symmetric, and transitive. That means it is an equivalence relation. A special note about equivalence relations: if R is an equivalence relation on X, and A is in X, then the class A, these little square brackets are class. Class A is the set of X such that X are A, where class A is a set of all the elements of X that are related to A, and A is called an equivalence class. Equivalence class given by the relation A. If P is equal to class A such that X is in A, then P is a partition of X. So let's take a look at an example. Consider a relation R on X where X R Y means that 3 divides X minus Y. X is all of the integers 1 to 12. How is X partitioned, and what is the equivalence class for? So let's take a look at S. It's going to be a set of sets where X minus Y divides 3, or 3 divides X minus Y. So let's see. I know one of my classes is going to be all the numbers that are divisible by 3. 3, 6, 9, and 12. All of those, if I take 6 minus 3, that's 3, that's divisible by 3. 9 minus 3 is 6. 12 minus 3 is 9. So all of those together is going to be one of my sets. 3, 6, 9, and 12. And then we can start to see a pattern emerge. Another set would be 1, 4, 7, and 10. So 4 minus 1 is 3. That's divisible by 3. 7 minus 1 is 6. 10 minus 1 is 9. 7 minus 4 is 3. 10 minus 4 is 6. So here we're seeing that combination again. 1, 4, 7, and 10. And then our last set is 2, 5, 8, and 11. So we're seeing all of these sets have numbers that are every third consecutive integer. Yeah, and that's how we make this relation work. Okay, so that is how S is partitioned. This is a partition. We're including all the elements of X. We're including them exactly once. So none of these 3 sets have any overlap, and we're including all the members. So that is our partition. What is the equivalence class for? That's going to be the set that has 4 in it. So that's this one. This is the equivalence class 4. That's the only one that has 4 in it. There should only be, if it's a partition, there should only be one that has that 4 in it. And there it is. I want to prove that R is an equivalence relation. So I'm proving that it is reflexive, symmetric, and transitive. So it is reflexive. Well, let's check it out. Reflexive. So for something to be reflexive, I am looking at XRX. XRX means that X minus X is equal to 0, which is equal to 0. Does 3 divide that? 3 divides 0, so XRX. So our relation is an equivalent, is reflexive. Let's look at symmetric. I want to look at XRY and YRX. Suppose XRY, and that means, that 3 divides X minus Y. So I could write X minus Y as 3n for some integer n. So let's look at what is what is y minus x. Y minus x is negative X minus Y, which is negative 3n. By multiplying this side by negative 1, I can also do it to this side, negative 1. Let's see. So then I can write this as 3 times negative n. And here I'm seeing 3 times some integer. So 3 divides y minus x. Thus y r x. So it is also symmetric. XRY means also YRX. Last one, transitive. I'm going to suppose x r y and y r z. So this means that 3 divides x minus y and 3 divides y minus z. So I'm going to let x minus y equal 3m and y minus z equal 3n, for n and m are both integers. Then what happens next? I can add these together. So x minus, oh sorry, I said x, but I wrote y. X minus y plus y minus z is 3m plus 3n. Let's see, if I add these together, these y's cross out, and I'm left with x minus z, which is kind of what I wanted, is equal to 3m plus 3n. I can factor out the 3 and write m plus n. So x minus z is divisible by 3. So that means xrz. So I've shown that it is also transitive. So since it is reflexive, symmetric, and transitive, R is an equivalence relation. R is an equivalence relation. Going back to the definition of what each of these things means in order to do this demonstration. You'll have several of these to do in your homework. We're going to do a couple more for practice. First, in example 3, we want to write the relation as a set of ordered pairs. Is it reflexive, symmetric, antisymmetric, partial order, or an equivalence relation? And here we have a digraph. Let's go ahead and write out what R is before we look at our digraph. R is a B, that's this one, and also BA, that's that one. It is BD and AC, that's these two. It is CD, and then also a loop here at CC. That is our relation. So first up, is it reflexive? It is not reflexive because we are missing several loops. I'll just say no, because AA, also BB, also DD are not in our relation. I would only need to show one of those. I want one counterexample. Here I've shown 3 counterexamples. Reasons why why our relation is not reflexive. Is it symmetric? I can look at it and see I would need this one, I would also need this one, I would also need that one, and I'd also need all the loops, so it's also not going to be symmetric. No, because BD is in R, but DB is not in R. That's one of the examples. Also, CA is not in R. DC is not in R. And so there are several reasons here why it is not symmetric. What about antisymmetric? Is it antisymmetric? Also no, not antisymmetric because of this relationship. No, because AB and BA are in R, but A is not equal to B. So not antisymmetric either. Last one, is it transitive? It is also not transitive, I think. No, and that's because, let's just pick one example here. AB and BD are in R, but AD is not in R. There are other examples I could have picked, but this is the one I'm going with. Another one would be BA and AC, but not BC. So it's none of the things. So that means it's not a partial order or an equivalence relation. It's not even close. Therefore, R is not a partial order or an equivalence relation. Neither one. Sad face. All right, here we are at our last one for this video, example 4. Determine whether each relation defined on the set of positive integers, so that's z plus, is reflexive, symmetric, antisymmetric, transitive, equivalence relation, and or partial order. Maybe we'll have some more luck with this one. So this one, I'm not going to be able to write down like the entire set, but I like to write down like some values that are in the set just to get an idea of that. So I'm looking at x minus y is equal to 2. And x is positive integers, so that's z plus 1, 2, 3, 4, 5, etc. So some values I'll write down over here. We'll have some values for x and some values for y. So let's see, x could be the absolute value. So if x was 3, y could be 1. Or I could actually do it the other way. X could be 1 and y could be 3, and then I'd get negative 2 and take the absolute value and get positive 2. Let's see, so I could do 4 and then 2, 2 and then 4. I could do 5 and then 3, 3 and then 5. So I'm gonna have all these pairs. So that's actually, as I'm thinking about this, it's probably gonna be really good for symmetry because I'm gonna have all these pairs. Okay, so I think that's all I'm gonna write down for now. That gives me an idea of what the elements of my set are gonna look like. So is R reflexive? Reflexive would mean that 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, none of those are in the set. So it is not reflexive. And I'm going to say that x is not in R because x minus x is equal to 0, which is not the same thing as 2. So it is not reflexive. Which means it's not going to be, so spoiler alert, it's not going to be an equivalence relation or a partial order. Both of those would require it to be reflexive. So already those are out, but I still need to check the rest of the properties. Is it symmetric? I kind of looked at that earlier when I was writing out my list. It does look like it's going to be symmetric. So let's write down y. If the absolute value of x minus y is equal to 2, then y minus x is equal, the absolute value of y minus x is equal to the absolute value of x minus y, which is equal to 2. So y r x. So it is actually symmetric, yes. Antisymmetric. It's not antisymmetric. Was this a double negative? I'll just say antisymmetric. It is not antisymmetric. That's because, let's see, well, I'll pick any example. 4, 2 is in R, and 2, 4 is in R, but 2 is not equal to 4. So not antisymmetric. Transitive is the last one. Is it transitive? Let's see, 1, 3 is in R, and 3, 1 is in R. So that would mean, well, I'll just pick an example here. 1, 3 is in R, and 3, 1 is in R, but 1, 1 is not in R. So when you do transitive, these middle ones match, and then the outside ones together have to be in R. So this one is not transitive. And I could have picked any pair in here because none of the loops, none of the x's are in the set. So it's also not transitive. So therefore, R is not a partial order or an equivalence relation. And that's it for this video. I will see you next time.